Morning, everyone. So this is another simulation that I'm going to provide a link on that shared Google Doc. The simulation I showed you yesterday actually allows you to study both concave as well as convex lenses. This one, although it's colored, it only shows me convex lenses on both sides. We've talked about here from yesterday's lesson, a convex lens here expects light rays to actually converge, light rays to actually come together. We would remember we have for a lens, we expect because of refraction, the real side is actually on the opposite side. In this case here, what they're demonstrating with this pencil here, again, it's not realistic like the pencil is actually giving off light source. Probably better if this were, say, a candle. The candle actually emits light. It actually shows many rays. It actually shines in many different orientations there. It's only the light rays that actually intersect with the lens that actually converge together. We saw we didn't need to study all the rays in total. What the simulation does here is it actually starts off using what are called marginal rays. A marginal ray here will actually take the sort of outer side, hits this edge of the lens, hits this edge of the lens here. What we did here is we did what's called a principal ray. A principal ray here is depending on how tall the candle or the object itself is. If we can move this object. More so depending on how tall or short this object is, we had done just sort of this parallel or not parallel. So in this simulation, you could play around with marginal rays. Marginals go right up to the edges. Principal rays, we did a ray diagram with these two rays. A parallel ray converges as if through the F on the other side. Remember, F is always halfway to the center curvature point. For this one, the image, right? These are real. This is a real image because we have the real light rays, solid lines here actually intersecting. So if I end up putting up a screen here, I'm going to get a nice reflection, a nice mirror image of my candle. Nice and clear, nice and crisp. For this one here, it actually depends on how close I am. So what's my object distance? As I slowly adjust my object distance here, you'll see that real image there respond. As I get closer than F, we're going to actually see, our light rays actually diverge. They're actually separated on this side here. And we're actually going to see there's no intersection on this side, but you will, if I put a screen behind you, you will see some sort of virtual image. It's upright and it's actually larger. They're doing instead of the dotted line. These are not real lines. This is just our brain playing tricks on us here. We think a line that has this trajectory would have come from an image having intersected at this point. So that's now a virtual image. The image is now a negative because it's on the same side as me. We expect light rays are supposed to go to the right, which the solid white lines here do. But if I put up a screen here, if I look through this one here, this is our typical magnifying glass example. Our real object, positive object, is producing a negative image that's larger than before. I now have a blown up image when I look into the shininess of the lens itself. What's nice about this one here, just sort of introducing you more to this, putting up a screen here. This one we can't really put up a screen. This one we actually need to look into the lens itself, and just like we had looked inside the mirror for virtual image, we look inside the lens for this virtual image. But more so here for a real image, when I really have light rays actually passing through, I can actually put up a screen. I think it's going to change it to a light source for me. Imagine this one here was still my candle. I'm still drawing my same two ray diagrams here. Here's a screen. It could be as simple as a piece of paper that I move back and forth. There are parts to this lens here that if my light rays haven't converged together, I'm going to get a blurry image. I'm not going to get a nice reflection, a nice picture of my lamp source. But I can just pull this back here. Where these light rays here actually come together, we actually have a nice uniform, pinpoint, nice crisp image of my light source there. So there is a certain positive image distance. I can put up the screen and I can image it. If I had still the candle on the simulation here, I would have a very clear image of the candle. If I go too far away, some of the light rays are actually starting to diverge. I'm going to get a blurry image of the candle. So you can play around with where the screen is. This one here, again, they're real images because there's actual light rays passing through it, and we can actually project it nicely on the screen. What's nice about the simulation here, let's go back to our regular candle analogy here. We can play around with a couple other things. In this case here, I can play around with the diameter of the lens. So that's going to be how tall the lens itself is. That's going to actually describe, maybe I can put it on the menu rays here. If I make the lens itself bigger, I may end up being able to bend more rays in. So diameter, I can make it larger or not as large here. It's only the light rays here that actually intersect that will converge. When it converges, I have a positive focus. Refractive index, this is something that glasses makers do all the time. They can play around with the material, not only just the band on both sides, they can actually play around with the actual index, the medium itself. Some medium, if it's really hard, Snell's law would say it refracts more than weaker medium. So if I have sort of lower and lower refractive index here, there's less and less bend. We see the image actually go far away there. In this case here, as I slowly increase the index here, we can cause more refraction in a smaller distance. And again, glasses makers can play around with what refractive index to do. This curvature radius here, I mentioned here, has to do with the bulginess, has to do with the sort of bend of it. That's going to push away the 2F point here. Technically, you can do two different curvatures, but for simplicity for us, we're just going to have the same curvature on both sides. So that curvature here can be, the radius itself can be a little bit smaller, or the other side here, the curviness actually can bends a little bit more narrow here. Basically, you need to assume that this follows with a full circle, and as that sort of became more shallow, it's because the circle itself actually got larger. That center of curvature point actually went much farther away. So hopefully that's another simulation that you can play around with. For today, we've done the ray diagrams already. I just want to revisit those mirror lens equation again with the 1 over f is 1 over di plus 1 over dou, and see how it works for a lens. So let's just get straight into it. We have our mirror lens equation. Sometimes they refer to this as a thin lens equation as well. The reason why it's a thin lens here, again, it's we assume that there's only one refraction. So when we do 1 over f equals 1 over di plus 1 over dou, whereas the other side here is magnification is negative di over dou equals I over ho, right? Exactly the same as we had earlier. Those two are on your formula sheets. Just be careful for a lens, just like for mirrors. The focal length positive always refers to the converging type. And if you remember the converging type for a converging lens is actually just like we demonstrated there, it's a convex lens. Whereas if it's a negative focal length here is actually a diverging lens. And in that case, there is actually a concave lens or biconcave lens. That was different from mirrors. A convex mirror was actually one that diverged. A concave mirror was actually one that converged. Just watch out for that. Aside from that, everything else is similar. So let's just do this here. Nice and simple. An object is placed 3 centimeters and forms, I guess I should say 3 centimeters from a lens, and forms a real image, one that you can project it on a screen, 2 centimeters away. I just want to know what type of lens this is. Is this a concave lens? Is it a convex lens? You could start off with a ray diagram, but this is just using the sort of the equation way of thinking about this. A couple of things I want to introduce to you here is, you'll notice object distance. Object distance is always positive. So even though technically for lenses, technically the positive side should be on the opposite side because the light rays are actually getting through, the object is always some positive distance away. DO will always be positive, that's your exception. It's going to form a real image, so we expect to have a positive DI, right? Positive means real, but remember for a lens, real is actually on the opposite side. We actually want to find our focal length. If our focal length ends up one sign, positive, it's going to be convex. If it's negative, it's going to be concave. That's the easiest way to analyze this. So let's go 1 over f equals 1 over di plus 1 over dou. So let's just punch through. 1 over focal length. 1 over di is a positive 2 plus 1 over positive 3. I don't technically like doing fractions, so let's just do it as decimals. 1 over 2 plus 1 over 3. Oops. Delete 1 over 3. So 0.833. Keep the full number in your calculator if you can. We're going to take a reciprocal of that, and that gives me a focal length of positive 1.2 centimeters. Positive means it's the converging type, and the converging lens here, if you remember, it's a biconvex lens. So let's just draw a picture just to verify here. We have a convex lens. Our object, I'm always going to put it on the left side just for simplicity here. Our DO is a positive 3.0. So that's our object, our candle, or whatever. Even though this is technically the negative side of the lens, the positive side of the lens is we expect the light rays to actually go through. The DO is sort of an exception here. We shine a light through. I don't necessarily know where the focus is, but it sort of comes together. The line through the vertex also comes together. It just goes straight through. Use a ruler for this. Ends up forming a real image. It's a positive distance, and that DI is actually a positive 2.0. So for basically all distances that come out of your formulas, positive actually means on the other side. Just treat the object distance as a exception. So that's how we tell here. We've figured out that it's convex. Let's move to another question here. Just give you some variation in questions. Let's go back to that candle. A candle is placed 15 centimeters from a diverging lens. So it's getting you to think about what shape that is. And that diverging lens has a curvature. We'll assume that the curvature is same on both sides of the lens with a curvature of 20.0. I want you to find the image distance. So find out where that image shows up. Is it positive, negative? Is it real or virtual? And the magnification. Let's throw in that high over ho, die over do. So again, let's just deal with the math of it, and then we'll verify it using our ray diagrams. So what I would do, just like we did in kinematics, see if you can go through and label which numbers are for which letters. So this one here, it's our candle that's being placed 15. It has to be positive. That's going to be DO. We're placed from a diverging lens. That word diverging indicates to me it should be a negative focus. So either they give me, either out of the math, it comes a negative number, or they give me the focal length. They didn't give me the focal length. They gave me the center of curvature. Remember, the center of curvature is 2f, which is 20. So I know f is actually going to be 10, but I'm going to need to come along and I need to put f as negative 10. Right? So negative means it's diverging. With that, let's try to find the image distance. You only have these two formulas, so hopefully we have enough information. 1 over f equals 1 over die plus 1 over do. Magnification is high over ho equals negative die over do. And let's just plug and play here. So we're going to go 1 over, I had purposely put in the negative, right? You'll still mathematically be resolve something with a positive, but it's just not going to give you the right answer. Notice that the distances here, we're just doing by ratio. Technically, I should put everything in meters, but since everything is centimeters, everything will cancel out as well. I don't know what 1 over die is, but I do know my object here happens to be at 15. If I have an equation where there's only one unknown, I can do it. So 1 over a negative 10, I'm going to minus 1 over 15. That gives me a negative 0.167. That's rounded. I'm going to do the reciprocal of that. Let's figure out where this image appears. The image appears at negative 6. When the image distance is negative, right away we can say it's virtual. Right away it means I can't project on the screen. So we're dealing with not actual light rays. And because it's not actual light rays, we cannot project on the screen. And when I draw the diagram, I expect it to be on the same side as your object, right? I expect light through a lens is supposed to get through, but this one here is actually back the way it came. This time here, that's also trying to find the magnification. If you know the die and the do, you can actually find the magnification. I don't actually know the height of the candle in this time, so I don't actually can do high over ho, but I can do magnification is negative die over do. I take a negative of the negative 6 that we just did. The object distance here was a 15. And this gives us a magnification 6 over 15. Magnification as a ratio would always be between 0 and 1. In this case here, because this is less than 1 here, we notice that the image is smaller, or what we say here is diminished. That's what the math tells us. Let's have a look at a ray diagram just to confirm here. So we have a principal axis. We have a diverging lens. So we already said diverging should be concave on both sides, a biconcave lens. Again, symbol-wise, you typically do like a inward pointing arrow. That's the symbol for diverging. I'm going to have my object distance placed at 15. So I'm going to be 15 positive away. So that's going to be DO. That's the one exception, because that candle here has to be a positive distance. Other than that, I would imagine light rays were supposed to hit this and actually go sort of diverge. They were supposed to separate. So in this case here, I would expect this is the virtual side of the mirror, and this is the real side of the mirror. Virtual side here should have negative distances. Real side should have positive, with the exception of D naught there. We're just going to draw a rays here. Hopefully I have an F. The F is actually at 10, so I have an F at 10. Again, do this with the ruler. So a parallel ray here is going to leave as if it had come through the F on my side. So my real light ray I'm keeping as a solid line. The line through the vertex is undeviated. The line that goes through the center is unchanged, and therefore I get our DI is negative. It's on the left-hand side. It's on the same side as the object, but my DI is a lot closer, and that matches up here. We're slightly smaller. We're about 40% of the height based on the magnification that we got. So everything matches up nice and neat, just to prove to you sort of the equation gives me the same analysis there. Okay, so continue on with another question here. This one here, the algebra just is a little bit harder because it doesn't seem like we're given enough information. Let's start off here. A lens creates an inverted image half as tall as the object. I want you to find an expression. Let's try to give you a hint here. Find an expression for the magnification and the focal length. So again, this one here, same equations, but we're given some less numbers. We may not actually be able to solve, your height is this or your image distance is this, but at least I can get the relationship between the two of them. So let's just go right ahead here. We only have these two formulas, the same for mirrors and lenses. We have 1 over f equals 1 over di plus 1 over dou. We have on the other side here, magnification is hi over ho equals negative di over dou. So we know those two expressions. Let's see what information we're given. So I'm told something is inverted. So what I would imagine here is the hi is probably negative, right? So if ho was the height of the object, the height of the image is actually negative. It's actually half as tall as the object itself, so that would tell me that the magnification is actually, not only is it negative, right, negative 0.5. I know previously I said magnification should always be a positive number. In this case here, they're just pulling out that negative here. That negative, just like we had just said, the high would have been negative. That negative actually just implies inverted. So that's a better way of looking at it than we did before. So we know we're inverted. It's going to be negative. The image is half as tall, so it's 0.5. That gives us a nice ratio between hi over ho. So if you know what the object's height is suddenly, the negative will then flip it. It's going to do upside down, but the high is only going to be half what it was earlier. That has to be similar to negative di over do. So we dealt with the inverted, we dealt with the half as tall, and we just want an expression for magnification. So we could actually find the magnification. Magnification is negative 0.5, and using that, let's see if we can back calculate here, and let's figure out what is the actual focal length. What is actually the distance between the vertex and the focus? So what I'm going to do here, because I'm not given any object distance or object height, nor do I care about them, let's just do the latter part here. I have a negative 0.5 from earlier. Again, the negative just means inverted. Negative 0.5 is supposed to be negative di over do. Now this negative here was in the formula. It just undoes the sign of whatever di is. And we find that that perfectly matches up. Negative cancels negative. 0.50 is now di over dou. I don't know either of these. However, I do have a relationship. The di is equal to 0.50 d naught. Right? So wherever I see di, I can actually sub in 0.50 d naught instead. I like it in terms of d naught because the object has to be a positive and it has to be somewhere. So if you know what the d naught is, if I come along later on and tell you the d naught, I know right away what the f is and I know right away what the magnification is. So wherever I see di, I can sub in 0.5 d naught. I see a di right here, so I'm just going to sub that into this expression here. So the expression, I don't have exact numbers or whatever to it, but at least expression-wise, 1 over f has to be 1 over. I sub in this 0.5 d naught. I plus 1 over d naught, like we did earlier. Just like we did 2 days ago with math here, 1 over 0.5 just becomes a 2, so that just top part just becomes 2 over d naught plus 1 over d naught there. This one here does have to be common denominator, so 1 over f is supposedly 3 over d naught. And in this case here, I can just isolate. I want an expression for the focal length. So I take the reciprocal. If you take the reciprocal fraction, it just upside down the fraction. So d naught over 3, or if you like, you can say a third of what d naught is. Right. So let's see if we can verify that here. You can probably figure out what type of lens it is, but we're just going to do that in a second here. We have the focus, and we have the 2f point. I have the focus, and then I have the 2f point here. For the image to be upside down and also half as big, your focus has to be a third of the way of what d naught is, which means d naught has to be 3 times the focal length. That means your object has to be somewhere out here. Let's try to draw those rays there. We draw a parallel. Notice that the di is also going to have the same sign as d naught, right? D naught is going to be some positive number here. Di is going to be positive. For di to be positive, the positive side is for lens is going to be on the far side. So we're expecting this is actually going to be an image on the other side. And what's going to happen here is the di is actually going to be halfway to the d naught. So if d naught was 3 times focus, so 1.5 focus, we would expect the image to be half as tall. We'd expect it to go through here, which matches up with our ray diagram. If I go through the focal length, that there ends up intersecting there. And similarly here, if I draw that line undeviated through the vertex, it's just going to cut straight through, and everything matches up. Because this is a converging lens here, the focal length also has the same sign of d naught, so focal length here is positive. I could have actually done that earlier here. Positive actually stands for convex lens. So there we go. We didn't quite have all the numbers to it, just a little bit more algebra for you to solve, but that's pretty much how you finish that off. I'm going to do one last question, just a more standard question. I haven't really recapped with you what happens if we actually know the high and the low. How does that come into play? Let's just try one more. Your worksheet will have a lot more of these style problems. I only have the same 2 expressions. They can play around with which variable is given, and you can just have a look at calculating for the other one. So a convex lens here with focal length. Remember, the focal length is the distance from the vertex to the F. Focal length of 18. Notice that's a positive. It forms a virtual image. It forms a sort of a fake image. It's not real light rays actually intersecting. It forms a virtual image at 5.0. Same styles of questions. I want you to find the magnification. Find out how blown up or diminished this one is. Find the magnification and the image height. Given the object or the candle, whatever's emanating the light here is, let's say, 2.4 centimeters tall. Alright, so let's just like before, I have a word problem. Let's see if we can go through and identify some features of this. A convex lens, we know it bulges on both sides. You should be able to say to me, a convex lens here is a converging lens. A converging lens here should have a positive focus. So when they have a focal length here of 18, vertex to F is 18, which means this is going to be a positive 18 for F. Perfect. It forms a virtual image. That now indicates to me probably it's going to be a negative distance. They gave it to me still as a positive number. I'm going to punch in di actually as a negative 5. Again, mathematically, you'll still be able to do it with the positive 5. It just isn't going to give you the right number. So make sure you interpret it. Make sure you put in the signs as we need. And we're interested in finding the magnification. The image height, given the object is this tall here, the object height here is going to be 2.4. Same 2 formulas. Hopefully you're not bored of them by now. 1 over f is equal to 1 over di plus 1 over dou. The magnification is high over ho equals negative di over dou. Let's just see what information we have. We have the focus, so this is going to be 1 over a positive 18 is equal to 1 over the image distance happens to be negative 5. I don't know what my DO is. I can use this to solve for DO. And with DO, I can probably punch it to my magnification formula. So let's try it out here. 1 over 18, I'm going to add the 1 over 5 over. So this is going to be 0.256 is equal to the reciprocal of DO. DO, no surprise here, should always be positive. So this is 3.9 centimeters. Object distance, make a note to yourself. Object distance is always positive. A little bit strange because this is actually the negative side of the lens, right? We expect the light rays to actually get through. And with that here, I can find the magnification. Let's first do magnification as negative di over dou. So the negative is in the formula. I take the negative of a negative 5, divided by my object distance that we just calculated as 3.9. It gives you here 5 over 3.9 gives you 1.3 as the magnification. So we're going to be scaled up. We're going to be 30% bigger than what we were before. Because I was given the height as well, I can now use this magnification. I can use magnification as high over ho. I can rearrange that if you like to find the height of the image. It's just the magnification times the height of the object. So this is going to be 1.3. The object they gave me was 2.4 centimeters tall. Magnification has no units. If you have the unrounded number, even better. 1.3 times 2.4. Give or take a little bit of rounding, I'm getting 3.1 centimeters. Right? So I just wanted to show you in this lesson here, everything is consistent with what we've been learning. Let's draw a ray diagram just to make sure this is all good here. So we have our principal axis. I have a convex lens. I know it's a positive focus. The focus itself is at 18. The object is only 3.9. So the focus is way out here, somewhere at 18. 3.9 would be somewhere down here. So this is my object distance. That's my DO. I'm going to draw my light rays here. The focus on the other side here, I can even say -18. Remember, this is the virtual side of the lens. This is the positive side of the lens. This is the real side of the lens. When I draw my light rays, it's a parallel ray. It refracts through F on the other side. One that goes undeviated is the one that's the vertex. If I can backtrack here, I should have left myself a little bit more room here. If I can backtrack here, it will eventually intersect somewhere back here. The distance of the image was negative, so that's why DI was actually a -5.0. Right, DO is always positive, so that's going to be positive nonetheless, 3.9. And we end up seeing the magnification. The image, it's a virtual one because it's dotted lines. It's not real light rays that are doing that, but the image here is positive, meaning that it is upright. Right, introduced to you, positive means it actually stands tall, and the 1.3 actually is the scaling factor. We're now 30% taller than we were to be before. Again, we use this for a typical sort of magnifying glass design. If I look through the lens material, although I may not be able to put a screen behind what I'm magnifying, if I look through the clear glass, I'm going to end up seeing the object here looks larger than before. So play around with some of those equations on the worksheet there. We're going to switch over to doing some relativity in the next lesson, and that'll finish up our waves chapter.